Alright, boys and girls, welcome back to the drive-through as we get into our little second installment of precalc. And this little mini unit is on vectors. Remember, a vector is like a ray, but it is not in the sense that it does not travel forever. Okay? It has a direction and it has a magnitude. The magnitude of the vector is described by the length of the vector. Okay? These are things that we picked up on in Algebra 2. So there are some things that we're assuming that you're coming to this lesson with. If you have never learned about vectors before, or you forget about them, then you might want to go back and just look at some of the basics of vectors. Like things like force, velocity, acceleration, I don't know how to spell that. These are things that are better represented by vectors, because the difference between this as a velocity vector and this as a velocity vector is understandable. I think this one is going faster if you wanted to use speed and velocity. And if you consider the difference between this as a velocity vector and this as a velocity vector, those two vectors are going about the same rate, they have about the same magnitude, but they're going in different directions. Okay? Now, the first thing we're going to learn about is called a dot product. And I want you to think about a dot product as like, what's it called? Like when you, like a compatibility score between two people. So if you can, we're just going to use a black vector and a red vector. You might consider these vectors to be completely compatible. They're the exact same vector. Okay? You might consider these two vectors to be utter opposites. And since they are utter opposites, they actually have a lot in common. They are completely polarizing. You'd be surprised. People that are like this tend to get along with each other. They have completely opposite views, but along the exact same spectrum. So this person might absolutely love cats, and this person might absolutely hate cats, and between the two of them, they'd have a lot to discuss. Okay? And then you could have a kind of a third relationship. And these two people actually have nothing in common. Okay? There is nothing that the red thing has going on that includes what the black thing has going on. They are literally 90 degrees from each other. They have nothing in common. So that's just how I want you to consider the dot product. Okay? When you take the dot product of two vectors, the result is a scalar. It's just a number. We are going to interpret that number to kind of understand the compatibility of these two vectors. So let's start with an example. Let's say that we have 5, 0 and -5, 0. Okay? So that's this one. We have this, and we have this. Okay, well the definition of the dot product is if you have this, x, y, dot a, b, that equals x times a plus y times b. Okay, so if we go into our example, that would be 5 times negative 5 plus 0 times 0. So if we did the 0 dot negative 50 the answer is negative 25. Okay? What does that mean? Well, if the answer is negative, that means they're traveling in the opposite direction. Okay, let's do another one. What if it was what if we had 5 comma 0 dot 0 comma 5? Well, that would be this example, right? And the answer is 0. 5 times 0 is 0, plus 0 times 5 is 0, and the answer is 0. So if you get an answer that's 0, that means they have no components in common. This one is all horizontal. This one is all vertical. They have no components in common. Okay, and then let's just do like a more common one. So let's do 1 comma 3 dotted with 6 comma 2. Let's take a visual look at what this would look like. 1 comma 3 kind of looks like, let's see. Let's put it on a number line. 1 comma 3 looks like that, and 6 comma 2 I think looks like that. Okay, so when you dot these, you get 6 plus 3 times 2 is 6, which is 12. Okay, so if it's positive, that means they have something in common. Okay, they are both traveling in the same direction. They have direction in common. So that's just how to find a dot product. The most important thing is that a dot product produces a scalar. And a scalar is just a number, so it doesn't have any direction. Okay? Now, we can use the dot product to find the angle between these two vectors. So here's your next fact. The cosine of the angle between the vectors is equal to the dot product of the vectors divided by the magnitude of the first vector times the magnitude of the second vector. So let's go back to this example. This is the vector 1 comma 3. Oops, I always do that. And this is the vector 6 comma 2. You will see that the angle between them is acute. Okay? The magnitude, so in this case, this would be u and this would be v. Again, if you remember, to find the magnitude of u, you just do the Pythagorean theorem. It's the square root of 1 squared plus 3 squared. So we write this like this. The magnitude of u, so the size of that vector, the length of that vector, is the square root of 10. Okay? The magnitude of the second vector is the square root of 6 squared plus 2 squared. That's 36 plus 4. That's the square root of 40, which is 2 radical 10. All right, so to find the angle between these vectors, cosine of theta is u dot v. Well, here's u dot v right there. It's 12 divided by radical 10 times radical 40. I'll just leave it like that. Cosine of theta is 12 divided by radical 400, Okay, how do I find theta? I take the cosine inverse. Let's go to the calculator. Okay, so we want to do second cosine 12 divided by radical 400, hit over, hit close, bam, and the angle theta is 53.1 degrees. Let's try another one. How about how about 2, 3 and 3, -2? All right, so what's the angle? If this is U and this is V, let's sketch something real quick. All right, 2 over 2 up 3. Okay, and the other one would be over 3 and down 2. Let's see what, doesn't look like those have a lot in common. Let's find the angle between them. Cosine of theta is U dot V over the magnitude of U times the magnitude of V. All right, U dot V. So that's going to be 2 times 3 is 6. 3 times -2 is -6. Magnitude of U is 4 plus 9, so it's radical 13 times radical 13 for the other one. Ah, watch this. So cosine of theta is 0 over radical 169. What kind of angle gives us 0? Cosine of angle, that means the angle is 90 degrees. Ah, that's why if you have a dot product that gives you 0, then the angle between the vectors is 90 degrees because of the cosine. Okay, now I'm going to show you one more formula, but I want you to understand what you're doing here. If this is vector V, and this is vector U, I'm going to teach you what's called the projection of U onto V. Now, the order matters here. So the projection of V onto U might be different than the projection of U onto V. But here's how I want you to imagine it. Imagine that you're taking a flashlight and you're shining it perpendicular to whatever we're going on to. So in this case, we would be taking a flashlight. Oh, I knew that was going to happen. Where did it go, Viv? And I'm going to start it from here. And you'd be shining this flashlight. I do not have the same art skills as Vivian, but imagine that that's a flashlight. It's shining light in this direction, okay? Then you would end up projecting onto V like that far. Could you imagine that? What that is, what we're really doing is we're figuring out how much of the U component is going in the V direction. And like if you can think about motion, that's going to be really important because we want to like take these into components. If you've ever drawn a free body diagram, that's what you're doing. Okay? So the equation for the projection of U onto V, the projection, this is weird notation, so I wanted to write it, of U onto V, that's how it's written in many math textbooks, is, you use the dot product, so it's U dot V, keep in mind, that's a scalar, that's a number, over the magnitude of V, that's also a number, so it's like a compatibility number divided by the entire length of the V vector, and then you multiply that thing by the actual vector V. So it's important, just like we see in our picture, the projection of U onto V is a vector. It results in a vector. And that purple vector tells us how much of the green vector is traveling in the black direction. Okay? And so I'm not going to do an example because this video is a little bit too long, but there is that on the homework. Once Vivian gets her homework done, I'll check it. I'll post that key because I'm sure it's going to be right, and we'll move on from there. Have a great day. Boom!